Our today experiment is motion in one dimension. It consists of two parts. Some of you may have watched the experiment before. Today, I'm going to explain how you should do experiment on the instructor video. This experiment is quite different from the others. There's a pre-recorded movie of a real car moving at a constant velocity. If you ask that this is a real experiment, my answer will be yes. This is completely a real experiment. The video given you contains a real experiment. We will take measurement on this video by using tracker software. After running the tracker, we will upload the two-car video we put on the report page to the tracker. Just drag and drop the video onto the tracker screen. This video is 15 frames per second. As you can see, the sliding of two cars on the rail was recorded. We have the same cars and rails in our laboratory. In later experiments, you will be able to record with your own mobile phones. You can also examine this movement by placing sensors on the rail. How? You put a photogate as a sensor between at least 2 points on the rail. Whenever the car passes through the sensor, a timing is obtained. So, time measurement is made. Based on this time measurement, the constant speed of the car can be measured. With this method, we get two data. First data is the time the car passed the first photocenter. The second data is the time the car passed the following one. Here, we can find the time between two photosensors. We find the distance between the two photosensors by taking measurements. From here, we can find the constant speed of the car from these two data. But our aim here is to get as much data as possible because the more data we collect, the more sensitive your measurement will be, the more real it is. All scientific researches are based on the same logic. Now, we will see how we do it in Tracker. For this, it would be appropriate to ask the question of what a video consists of. A video consists of frames. Our mobile phones can take at least 30 frames per second. This means that when you take any video, 1 second view of this video consists of 30 separate frames. So, actually, 30 pictures are taken in 1 second, then they are played using a video player program. Then you can play the movement frame by frame. This allows us to measure where the object is at each frame. We can do this by playing the video frame by frame. If we examine the movement of the card below, Let's say we will measure its speed. For this, we need to measure its position at certain times. That is, we need to collect the position time data. I will try to teach you how to measure position and time data in each frame. Firstly, we must define how much distance in the program corresponds how many centimeters. For this, a squared meter stick is placed where there is movement. In this squared meter, each square is 10 centimeters. In other words, the ruler is exactly 1 meter tall. To introduce this, we click on the calibration stick. After clicking this, we need to define 2 points for the calibration stick and say 1 meter between this point and this point. To define the first point, we hold down the shift on your keyboard. As soon as we hold down the shift key, the mouse cursor becomes square. To place the first point, we click the left button of the mouse while holding down the shift to determine the first point. While holding the shift, we click here again with the left mouse button. The program connects those 2 points with a blue line. Now to define that this line is 1 meter, we click on the place that says 626 meters. Write it is 1 meter and press enter. We've now created the scale. Since we need a certain reference point, I mean origin, in order to be able to measure the position, we must place the 0 point of the coordinate system at the point we designated as the origin. To do this, we first click here to place the axis. Since we want to examine the movement of the card, which is below, we must place the axis at a certain point on the card. We place the origin of the axis exactly in the middle of the yellow label, because the yellow label on the card provides us with ease to track the movement of the card. In order to determine the exact middle point, zoom is done with the mouse wheel. The squares that appear on the screen are called pixels. The width of a pixel is the smallest distance that can be measured. That is, error or uncertainty in position measurement. Now let's see how the pixel width is measured. For this, we click Create Tab, Measuring Tools, Tape Measure respectively. We place the ends of the arrow on these 2 points to measure the distance between the 2 points we have specified. We can increase the thickness of the arrow to see our measurement more clearly. The division of this distance by the number of pixels between 2 points will give us the width of a pixel. When we count the pixels, we see that there are 8 pixels. If the width of 8 pixels is 1.278 times 10 to minus 2 meters, approximately 12.8 millimeters, the width of 1 pixel is found from 12.8 millimeters divided by 8 is 1.6 millimeters. The Create tab is used to introduce the object that we will measure on to the tracker program. Since we will examine the translational motion, the object is defined as a point particle to the system. Mass A is clicked to select the name, and the object is named as cart manual track. We are now ready for position measurement. For this, a distinctive region must be selected on the object. The yellow label on the card is suitable for this. While holding the Shift key on the keyboard, the first position is measured by left-clicking with the mouse. If we remember, we also tried to select the origin in the middle of the yellow label. Since we choose the first position at this point, we expect the first position to be 0. When we look at our measurement, we see that this value is 9.301 times 10 to minus 5 meters. That is approximately 0. The position in the vertical y value is reported by the system. However, since the position of the object in horizontal is observed in our experiment, the value of y will be not considered. The position is automatically associated with time by the program. Because the playing speed of the video indirectly includes time information, this video play speed is 15 fps. That is, the video image with a length of 1 second consists of 15 separate frames. From here, by using simple proportion such 1 divided by 15, the elapsed time between each frame is recorded to the system as 0.067 seconds. Video jumps to the second frame immediately after the first position measurement. The position measurement in the second frame corresponds to the position at 0.067 seconds. The position measurement in the third frame corresponds to the position at 0.133 seconds, and this continues sequentially. Position timetable and graph occurs simultaneously with clicks. There are different options for the position markings in the program. You can review the tools. Since three types of graphs can be used to represent the motion of an object in one dimension and the motion of the particle on the x-axis, we can also examine the x-component of the speed. For this, Vx is selected by clicking X on the graph. The data in the graph corresponds to the instantaneous speed values. These speeds were obtained by the program by calculating the average speed using the position data between two frames. Note that there is no data at the 0th second. The program obtained the instantaneous speed at 0.067 seconds using the average speed formula x1 minus x0 divided by t1 minus t0. Similarly, the instantaneous velocity value at 0.133 seconds is obtained by using the average velocity formula x2 minus x1 divided by t2 minus t1. By clicking X on the vertical axis and selecting the X component of the acceleration, namely AX, the acceleration time graph can also be seen. Since we define the motion in terms of space and time, it's important to tabulate the position, velocity, and acceleration values versus corresponding time values. For this, after clicking on the table, these quantities should be selected to see the data in a single table. The image of this table should be included in your report. Right-click on the table and choose Analyze to open the Data Tool screen. The open screen data is used to analyze the data graphically. On the screen, there are a table of the position data of the card at various times and a position time graph for this data. Curve fits are selected from the Analyze tab to plot graphics. As can be seen from the table at the graph, the cards makes equal displacements at equal time intervals. That is, it moves at a constant speed. Since the position time graph of the constant velocity motion is linear, fit name should be selected as line. Parameter A in the fit equation corresponds to the slope of the line best fitted to the position time graph by the tracker. This value is constant velocity of the cart, which equals to 7.218 times 10 to minus 1 meter to second. That is approximately 722 millimeters to second. The meaning of RMS dev on the screen is the root mean standard deviation. Since the vertical axis contains position information, this value corresponds to the uncertainty in position measurements obtained from position measurements. This value was calculated by tracker as 5.492 times 10 to minus 4 meters. So, in this experiment, the uncertainty in position measurement is approximately 0.5 millimeters. This value is quite small. We want you to add this plotting with the parameters to your report. Now we will analyze the movement of the cart by using velocity versus time graph. To do this, we click on X on the graph and choose Vx. Each data in the Vx versus t graph corresponds to the instantaneous speed value calculated by the tracker using sequential position measurements. These data are combined by a line by tracker. Since the movement of the cart is constant, we expect this data to locate on a straight line. However, when we look at the graph, it is seen that they diverge from the line. Actually, If the graph is scaled as Vx equals 0, it can be understood that these divergences are minor. The reason of these divergences are the uncertainty of the position measurements. To find the error of these deviations, we again click on Analyze on the graph and open Data Tool screen. Since this time we want to find out how much the data diverge from the average velocity, we choose Statistics on the Analyze tab on the screen. This value is the constant velocity value acquired by calculating statistical average of the instantaneous velocity values, which are obtained from the position time values calculated manually. This value is equal to 7.223 times 10 to minus 1 meter to second, namely around 722 millimeter to second. As expected, this value is so close to the value obtained from the slope of the position time graph. If we continue to analyze the table, SA means standard error. The value here is the standard error of the constant velocity and is equal to 1.852 times 10 to minus 3 meter to second. Namely 1.852 millimeter to second. If you add this value to and subtract it from the mean value corresponding to the constant velocity, you obtain a maximum and a minimum value respectively. You will see that all the data place between these extremum values. If you have questions about which value to use, the constant speed velocity acquired by using position time graph, or the constant speed value acquired by statistical analysis of speed time graph, I can surely say that you can use both. Minor differences are the result of using different methods while getting the values. If we decide to use the constant speed value obtained by using position time graph, you should calculate the uncertainty of the speed. Here, delta V, delta X, and delta T mean the uncertainty value of velocity, position, and time respectively. As we said before, delta X value is equal to RMS deviation value. You can get delta T value from the data tool screen. To do this, you should displace axis by choosing T on the x-axis. In this case, since time will locate on vertical axis, RMS deviation will correspond to uncertainty of time. But don't forget to check that auto fit option is chosen. As we said before, V value, namely parameter A, is the slope of the best curve drawn by tracker. Here, X and T value are the maximum value at position and time. By writing these values on the equation, you can calculate the uncertainty of the speed calculation. When we go back to what we last talked about, the equivalent of this value in this method is this value. We want you to place the image including the statistical table and the graph you get in your report. The things we have done so far are analyzing a real movement. The things we have done so far are analyzing a real motion. By the help of tracker software, we can do also modeling. The rest of our experiment is to be about modeling. To model the constant speed motion, we should choose kinematic model under Create tab. In order to give a name to model A, click on it, choose name, and name it as cart model. We choose the color of the model card, blue, in order not to confuse it with the cards belonging to the real experiment. To create model, we select Model Builder. We add parameter x0 and V0 on the opening screen. These parameters are the first position and constant speed value of the model card respectively. Since the movement of the card is on x-axis, we should enter the constant speed equation for the position on x-axis. In order to compare the motion of these two cards, we choose the footprints of the cards as bold vertical line. Since we are going to analyze the model card, we choose card model on the graph on the right. To make the modeling, we click on the card model and model builder on the left respectively. On the opening screen, by estimating a velocity value, we introduce the motion of the model card to the system. Assume that the velocity value is 0.71 meter per second. We have introduced the motion of the card below to the system by manually tracking for each frame. So, we can compare the motion of both cards by clicking on play key while the video is running frame by frame. The motion of the model card and the real card should overlap to each other as far as possible so that the modeling can be successful. At this stage, we try to achieve the motion of these two cards to overlap to each other at the optimum level by changing V0 value. We observe that the motion of the real card and the model cards differ from each other, especially at the last frames, at 0.71 meter per second constant velocity value. Let's write another value as V0 value in order to check whether we can obtain a better overlapping. And as a result, we see that the overlapping increases. This means that the consistency of the motion of the two cards increases. When we increase this value to 0.723 meter to second, which is more precise, we observe that the consistency decreases a bit. When we change the value 0.722 meter to second, we see that we get better consistency. To see this consistency on the graph, we click on the graph on the right and choose Compare With. Since the thing we want to compare is an experiment card, we choose Card Manual Track and click OK button. Now we can compare the data belonging to the motion of the cards on the position time graph. We can observe that the data points differ from each other a bit by zooming on the graph. We compared card model and card manual and the vice versa. For card model, we should create the table containing position, velocity, and acceleration data at certain times. And add the image of the table to our report. The position time graph of comparing cart model and cart manual track should be passed on figure 6. To plot velocity time graph, we click on X on the graph and choose Vx. Since this graph includes instant velocity data of both cards, we can compare the instant velocity of the cards graphically using this. We observe that the velocity data of the model card locates on a straight line. This means that speed don't change with time. Since these data belong to a model, this situation is expected. Likewise, the deviation at the velocity data of the real experiment card is not surprising. The reason of these deviations are the errors we make while carrying out position measurement. When the graph is rescaled, showing Vx equals to 0, we see that the deviations are minor and the card's motion corresponds with each other. We want you to add this image to your reports too. You should also add the image of the screen on which you have created on your kinematic model to your reports. You should pass this image on figure 8. Now, we are going to analyze the consistency of the real cards and the model cards quantitatively to see whether we have created a really successful model. To do so, we choose Tape Measure under Create tab. Name as Tape Measure. To define the ends, select Attach Ends from Tape Measure. This option helps us to measure the difference of the position of the two cards. We choose end 1 and end 2 as card manual track and card model. Each data on this graph shows the difference the position of the model and the position we have measured. In order to analyze the graph, we open Data Tools screen. Then we choose Statics under Analyze tab. The value here shows the average difference between the measured position of the experiment card and the position of the model card. This value is found 1.13 millimeters for this example. Since this value we have gotten is lower than the value 1.16 millimeters, which we have measured as pixel width, we can say that our model is a successful one, because pixel width defines the uncertainty of the position. Since the average difference is lower than the uncertainty, it can be said that the model is successful. You should also add the image of this graph to your reports too. I think you have an idea about how to prepare your reports to some degree so far. Nevertheless, I want to explain how to prepare your reports. First of all, you should open Submit Report to under Lab Report Submission tab. On Physics 1 web page, on the opening screen, click Report Template to download. Don't forget to answer the pre-lab questions here. If you want, you can reach the instruction video explaining how to do the experiment here. The images appearing on pre-experiment template should be changed with the images of the experiment you have carried out. Likewise, the results appearing on the template should be changed with the results you have gotten during your own experiments. All of them should be changed with your own results and images. As result part, you should answer 3 questions and you should discuss your results and conclusion part, and finally the question at the end of this part should be answered.